triangle. We have a triangle ABC, and we draw the three midpoints. So MA, MB, and MC. Hold on a sec. So this is MA. I'm just using the notation in the problem. MB and MC. And then we draw the circumcircle of ABC. And the ray MBMC meets it at a point P. So, all right. Thanks for participating, Irajan. So yeah, I'll check out the problem that you sent sometime. So this is point P. And then AP and BC meet at a point Q. And prove that the tangent at A, so we want to draw the tangent at A to the circle, and the tangent at P to, okay, so we need to draw another circle. So PQ, okay, so we want to show that these two tangent lines concur on BC. All right. Let me hide some stuff. Maybe it might be best to show. Yeah, like I could draw the intersection of two of them, and then we want to show DP as tangent. That's one way to do it. So I think I'll just stick with trying to do it that way. All right. So we want to show that DP is tangent to this circle right here. So we want to show DP squared is BQ times DMA. I wonder if these 4 points are in harmonic conjugation. No, they can't be. I wonder what point. So I think DB times these. Actually, I'm not sure now. Yeah, it's interesting. See who's still on. Sorry, just checking. Let's see. This problem feels a little bit easier, doesn't it? Let's see. So yeah, I wonder what points in harmonic conjugation with D, B, C. Is it just the angle bisect? Yeah, I feel like shouldn't that be a well-known point? Like what points in harmonic conjugation with D, B, and C? Just trying to figure out what point that is. Is it the median? Yeah, so if the Semidian is basically in harmonic conjugation with D, B, and C. So yeah, and it looks like the Semidian passes through this point, right? So it looks like basically if I label this point right here, then we want to show that AH is a Semidian, and then AD, AH, AB, and AC are in harmonic conjugation. And so if we label this point, DI times DMA is equal to DB times DC. Okay, so this is kind of interesting. So I'm going to hide all this stuff, except for this maybe. So is it obvious that AH is a symmedian?
Yeah, we project through A.
Okay, so if we project through A, maybe onto,
Wait, how did we define AH?
so H is the intersection of these two circles. So I'm going to delete point E and F. So I drew the circumcircle PMQA in the statement, and I let it cut the circumcircle of ABC at H. And then we want to show AH as a symmedian. Let's see. And once we show that, then we would know that if we label this point right here, then DE times DMA is DB times DC, which is DA squared. So then that would mean that this circle is, the circle through these points would be tangent also. I'm not sure if that helps much, but it was just something interesting I noticed. Feels like there's probably a good chance it's related. So we would have DE times DMA is DA squared. Then we want to find DQ times DMA and show that it's DP squared. So basically we would want to show that DP squared over DA squared is DQ over DE, I think. Yeah. Interesting. All right. All right, let's see. I like this strategy, but I'm still trying to think through it. So yeah, we want to find like what is dP squared over dA squared. So that's the ratio of the powers of those two circles. So now I'm thinking about the power ratio lemma, but that would be crazy to apply the power ratio lemma here, but
cyclicity is just angle chase. So we can calculate PHMA.
PHMA. Oh, to show that this is cyclic is just an angle chase.
Yeah.
Well, no. I actually defined. I guess then you're saying showing that AH is a symmedian is an angle chase.
Yeah, if AH is symmedian, then we can prove from angle chasing that H is on the circumcircle of PQMI.
Okay.
MA.
All right. So then once we know that D, B, E, and C are in harmonic conjugation. And so there's a theorem from that that says that dB times dC is dE times dMA, and dB times dC is dA squared. So we have dA squared is dE times dMA. And we want to show that dP squared is dQ times dMA. All right, so let's see. So dA squared over dP squared. I wonder, that looks a lot like Steiner's theorem, kind of. So P is the midpoint of AQ. So that's actually, yeah. Okay, so that's the angle chase. So PHMA is 180 minus A minus BHA minus PAB, which is AQMA. Okay, and yeah, and P is the midpoint of AQ. So I think like dP squared over dA squared, isn't there some theorem about that if P is the midpoint of AQ? I think there is, or I think it's like maybe we could apply like Apollonius's theorem or something, but I think, let's see. Yeah, let me try writing this down, but I think we're really close. So I think my idea should kind of lead to a solution. I wonder if Q is the midpoint of D. No. I'm going to write out some calculations on my paper. So okay, so I'm going to start writing out what we've sort of mentioned, and I have some confidence that it'll help us out. So let the asymedian of triangle ABC meet the circumcircle at H. And then from what Sir Gar said, we have angle PHMA. It's 180 minus A. Just trying to think. (180 minus A minus C). AQMA. I'm just trying to understand this. So PHMA. So I'm trying to, so 180 minus A, it would be 180 minus A minus CHMA, right? So CHMA is BHA yeah, I'm trying, so how did you get
BHC equals to 180 minus A. Then MAHC equals to BHA.
okay, so
So it's median.
okay, so
So I wrote
I see.
BHC minus MAHC, which is equal to 180 minus A minus BHA.
I think I see what you did. So you have angle PHMA is angle BHP plus or it's angle BHMA. I'll do it like this. Angle BHP, which is equal to so BHMA is angle CHA. And angle CHA is angle CBA. CBA minus angle BAP, and that is angle that's angle AQB. So I'll fix this. That's angle PQMA. Here we go. So PQHMA is cyclic. And once we know that, then we have that AB, AH, AB, AC are in harmonic conjugation. So AH is a symmedian. That means that E, C, E, and D are in harmonic conjugation by a well-known theorem. And so that means that dB times dC is equal to dE times dMA squared. I'll write it like it. dA squared is equal to dB times dC is equal to dMA. And okay, and then we want to show we want to show dP squared is dQ times dMA. But DP is a median in this triangle because P is the midpoint of AQ. So yeah, I'm just thinking about that. Maybe it might even help to draw a parallelogram here. So we want to show dP squared over dA squared is dQ over d. So dQ over dE, like we could write that as in terms of sine. So that would be like sine dAQ over sine dAE, I think. Let's think about that. Oh, that would be AD over AQ times the ratio of the sines of those two. Yeah, I think I see a way, maybe using like some trigonometry to finish this. Let's see. But let me see if I can write it out more elegantly. So we want dQ over dE. And those are if you look at the triangles ADQ and AD, yeah, maybe we could use projected geometry. We just want dQ over dE over dQ. So if you look at QCE, I wonder if that's the right. And or maybe DQEMA. See. Are these 4 points of harmonic conjugation, DQ, E, and MA? Let's see. I'm just going to check this really quickly. No. Can I draw the circle D, A, M, A, H? A. Yes, it's thick. Okay. So yeah, you knew it was cyclic. Yeah, I think that will help because DQ So I think if DP were tangent to this circle, then we would have, I think there's a certain relationship. So if we let P prime be the tangent from D to the circle, then we have dP prime Q is similar to dMA P prime. And I think there's a way we can combine those ratios. I forget what it is, but I think we can take dP out of the equation, and I feel like that would help a little bit. So let me write this out. So dP prime over P prime Q is equal to dMA over P prime MA, and then we would have dP prime over dQ is equal to dP prime over dQ is dMA over MAP prime.
Intersection of DP and ABC may be special.
The bisection of the fact that P is the midpoint of AQ, or
No, we intersect DP and circumcircle of ABC. It may be a special point.
okay. Yeah, I wonder if AF is parallel to BC. Let's see. So actually, I'm not 100% sure. No, I don't think AF is parallel to BC, but
Is it on MAB? Yeah.
yeah. So we could try to
I
find.
think they are not collinear.
Oh, really? F these 3 points?
No, they are not.
Oh, you're right. It just looked like it. All right. Maybe I'll just still leave it there. Just, I don't know. But there's a certain theorem. I think it's like, isn't dP tangent to the circle only if like PMA over PQ squared is DMA over DQ or something like that? Okay. Well, so we want to show that PMA over PQ squared is DMA over DQ, I think. I think that would.
But I think it is hard to find PMA. I tried to find it, but it's not hard.
So PMA is difficult to find. So PMA, it's a median in AMAQ. I don't know if that helps or it's still just as hard. Let's see. So I'll spend like another 2-3 minutes on this, and then I'll move on to the next problem. Actually, I'll move on to the next problem right now. We can get back to this later. Looks a little tricky. Are you guys okay with that?
Yeah, that's okay.
All right. Okay, so we have the triangle ABC, orthocenter H and circumcenter O. Whoops. This thing drives me crazy. Oh, that's because the C is not capitalized. A, B, C. So we draw, so the exterior angle bisector of BAC meets the circle at the midpoint of the arc. So I could just let N be the midpoint of arc BAC. And so that's N. D is another intersection of HN with the circle. All right. And the line passing through O, whoops. Sorry. So let's rename this D. And then the line passing through O parallel to AN intersects AB and AC at E and F. So yeah, let me make something more like this. So AB at, it already says E. E and F. And I want to show DH bisects angle EDF. So this feels very projective. This problem, it doesn't feel as hard. Hopefully I didn't jinx myself and it'll be hard, but seems probably not as hard if I had to guess.
Can you draw the midpoint of arc BC not containing A?
Yes, so that's the midpoint right there. Feels kind of like Pascal's theorem because we have DE and DF like this. Maybe I should let DE and DF meet the circle. And
we have a 90-degree and angle bisector. We can use projector now.
Yeah. Oh yeah. So basically, yeah, this is a harmonic bundle. So yeah, we want to project onto maybe we could try projecting onto the circle actually. So let's see where these meet the circle. And it looks like maybe they meet the circle. Like it looks like maybe IJ is parallel to BC. Yeah, I think, but yeah, that would have to be true. So yeah, if we could show IJ is parallel to BC, that would solve the problem, right? Because then by projective geometry, we would know. Yeah.
We didn't change the problem too much. It's the same as after noticing N is the midpoint. If DN is angle bisector, then BI equals to CJ arcs. So we didn't change too much.
Oh, is it obvious that BI equals CJ?
We have to prove that, but
Yeah.
it's easy to see from n is the midpoint. So projective didn't help too much.
Oh,
Maybe we should project to something else.
wait, is it, hold on a sec. Is it obvious? You're saying it's obvious that BI is equal to CJ?
No, it's obvious that we have to prove that, but not
Oh,
from projective, because
okay.
we know n is the midpoint.
But it looks like I is actually the antipode of C. So, which is, yeah. So yeah, we just have to show angle IBC is 9. Wait, this is looking, yeah, we need to show angle IBC is 90. Maybe we could try Pascal's. So B, BDC and IAJ. So BDC, IAJ. Okay. So yeah, IC and BJ have to concur on EF by Pascal's, right? So yeah, by Pascal's theorem, we don't know it's at O, but we know that IC and BJ have to concur on EF. And we know EF passes through O. So yeah, it feels like it should be trivial, but
Oh, we have to prove that BDF is 90 degrees. Maybe we can draw altitudes.
did you say BDF is 90?
Yeah, we have to prove that. So we can use altitudes maybe.
Yeah, because we want to show. Okay, we want to show BDF is 90 degrees. Let me see if there's like a cyclic. Yeah,
Can you
because
draw altitudes?
it looks like it intersects. Oh yeah, this would be like the altitude. So you want me to draw the altitude from B and C to the?
Yeah.
Yeah. Okay, hold on just a sec. Yeah, it feels like it should be obvious. Angle BDF is 90. So do those really concur? That almost looked like it. Yeah. Okay. Um, let's see. So we don't know yet that it's cyclic, but let me draw the circle just to kind of see. So yeah, we want to use the parallelism. We want to use the parallelism to show that so we want to show angle KFB is equal to angle KDB. That's one way to do it. Maybe there's a better way. I'm not sure. I wonder if D isn't the point of tangency of the mixed delinear in circle, but it's like something similar.
Midpoint of HN may be useful because it's on the circle.
The midpoint of DH?
HN.
The midpoint of HN?
Yeah.
Okay. So yeah, so that lies on the 9-point circle, right? Maybe I should draw the 9-point circle. So,
yeah.
So this is the 9-point circle. So this is the midpoint of HD here. But wait.
Actually, I tried to use that M is on the circumcircle of BDK.
Wait, sorry, that's not I didn't draw it right. So the 9-point circle should be on K, M, and L. There we go. So this is the midpoint of HD. This is the midpoint of BC. So yeah, if we could just show that BDJ is 90, that would solve it. Is EDGF cyclic? Yes. So yeah, we want to show angle BDF is 90. I'm going to draw that circle again. So maybe we could show, so we know BKF is 90, and maybe we could show BDKM is cyclic. So we want to show BH times HK. Oh, that would, once we know that, yeah. So basically we want to show DLMC is cyclic, I think that might be it. Yeah, if we could show DLMC is cyclic, that would solve this. DL.
That's power of a point because reflection of H across AB is on the circumcircle.
So you could show that DLMC is cyclic. So,
yeah, but after that, how do you prove?
because once we know that DLMC is cyclic, then DH times HM is HL times HC is HB times HK. So then DLMK is cyclic. And we also know that F, wait, so let me think about this. So DLMK, I forgot what I was doing here. Wait, so we would know that okay, yeah, we want to show DBMK is cyclic. So we would have BH times HK is CH times HL. Yeah, so once I could show that DLMC is cyclic. So how did you get that DLMC is cyclic?
What?
That DLMC is cyclic?
The reflection of H across AB is on the circumcircle.
Okay. So that proves that DLMC is cyclic?
We use power of a point, but we divide by 2.
Oh. Okay. Yeah. Okay. I think I got it. So I think that is enough to solve this. Let me
But
start.
how did you prove that F is on the circumcircle of DBMK?
EBMK, or F is on the circumcircle of BMK. Yeah. So how did I prove that? Yeah, DBMK. So let me think about that. So oh yeah, okay, I need some kind of so I would want to show that angle DFK is you want to show that DFK is 90, right? I want to show that DFK is 180 minus DBK, and DFK is DFE plus plus AFE, and DFE. Is there any way I can get that? DFE is DFO. Yeah, I'm not sure. Whoops. Whoops. So yeah, we have the DBMK is cyclic. And then can we show F? Right, so what did we want to show? We wanted to show BDF was 90, right?
I think we should change the approach.
We should change our approach.
Yeah, circles don't give anything.
But yeah, we've discovered so much. Like, yeah, we want to show, so I'll delete some stuff. But if we could show, yeah, because we kept using point M, I guess. I'll leave the 9-point circle in there. But yeah, it seems it shouldn't be hard to show that angle BDF is 90. It seems like a very like fundamental fact. I'm just not sure how to show it. Feels a lot like a problem I did from Evan Chen's channel, kind of. One sec, I'll be right back. All right. Yeah, so yeah, we have by Pascal's, CI and BJ meet on EF. We just have to show that the point that they meet at is O. But maybe we could use Pascal's again somehow. I'm just thinking. Because C, like if we could show GN, IC, and BO concur, yeah, can we show that GN, IC, and BO are concurrent by Pascal somehow? So IO, let's see, IC and GN meet at O, ID and AB meet at E. So let's see, BGC, oh, we would need like to draw IG, I think. Let's see. Yeah, what would the 3 points be? GC, A, yeah. Does AE equal AF? So AE equals AF, right? Yeah, because of the parallelism. So yeah, we want to use, I think, also that AE equals AF. I think we're close on this, but So AG is obviously an angle bisector. Oh, maybe this point we could use right here. So if the problem were true, then DERF would be cyclic. So yeah, maybe we could define R to be the intersection of AG with DN, and then we want to show DERF is cyclic, and that would solve the problem. But it turns out G would also lie on that circle. So can we show DEFG is cyclic? Is that obvious? Let's see. So yeah, can we show, so yeah, we want to show that all these points lie in a circle. Is it obvious that DEFG is cyclic? Would that be an angle chase? So I think GF, because G lies on, okay, so angle GFC is equal to angle GEB, actually, I'm pretty sure, because G lies on the angle bisector. So, yeah, so I think that shows, so we want to show GFC is equal to GDE, but GFC is equal to GEB. So we want to show GEB, but basically we want to show DEB is AEF. Is that obvious? AEF, is that even true? No. What was I thinking? Or is it? Yeah, my brain is just not working today. But yeah, I think this might be the right idea. Okay, so we want to show DGEF is cyclic. That's the same as saying GD 180 minus GDC is GFC, which is the same as saying 180 minus GDE is GEB. So we want to show GEB plus GDE is 180. So I wonder if You guys want to move on to the last problem and then see if we can come back to this? Let's just see if the last problem's easy, and then I'll. Oh, I think this one is kind of tricky, actually. Let's stick with this then. I wonder if R, K, and L are collinear. No. Yeah, I feel like one more application of Pascal's. Oh, whoops. Sorry. Hold on just a sec. Hold on just 1 second. All right, so all right, yeah, we have to use the parallel condition somehow. I'm just having trouble using that. So, I mean, really, it just means, so AEF is isosceles and passive through O. Yeah, I know this problem, it feels like it can't have that hard of a solution. It's driving me crazy. Like there's so many different things. If we show that VDF is 90, that would solve it. So yeah, we can show BDMK is cyclic by power of a point. We just need to show F lies on it. So Okay, we want to show that F lies on BDMK. We have to use a parallel condition. Is there any way we could use Pascal's combined with the parallel? Let's think. So yeah, we want to show that this is harmonic. Yeah. So we would have BDF, and we would have all three of these circles, really. CDEM, CDEL, or CDEM, CDELM. DEGF. So angle GDE. Can we calculate angle GDE? It's 90 plus angle EDN. Actually, if we can show EDGF is cyclic, that would solve the problem. Because then angle EDG would be, yeah, if we can show EDGF is cyclic, that solves it. So maybe I'll just write this out. Suppose we know EDGF is cyclic. Then angle EDG, or I'll say EDN is EDG minus 90. Which is angle EFG is equal to 180 minus GEF minus 90. And that would be and that would be 90 minus FDG. and that would be angle FDN. Okay, so I know we're over a little bit. I feel like we're close here though, so let me see if we can finish this off. Just wait another like 3 minutes. So is this just, because we know EF is parallel to AN, and we know DGAN is cyclic. So yeah, I wonder if that does it. So actually, I think it's not that simple. Yeah, because we haven't used that H as the orthocenter. Okay, maybe it's a little trickier than I thought. All right, I think we're close, but since we're out of time, I think I'll stop here. So yeah, these are definitely pretty hard problems. So for those watching on YouTube, if you like this, give it a thumbs up and subscribe. And thanks for watching. See you all next time.